Jeph, I don't know. When do we start thinking about introducing metal additive manufacturing?
So, Elena, I'll start if you don't mind.
Yeah, it's
and then
fine.
so it's always a tricky subject, right? Because you have a new process and you have potentially new materials that would have been otherwise unweldable, or historically we're working with a lot of casting materials. As far as when to introduce metal additive into your process, I kind of break it down into four sort of key reasons why additive would be the right tool to solve a problem. Ultimately, we want to use it as another tool in the tool chest to solve some application problem. It shouldn't be used as the new sexy option just for that. So the four sort of places that we go with it. The first is there a functional improvement that we can gain on a given application by using additive? So some typical examples of this, in the orthopedic industry, we can build in a monolithic porous structure, lattice structure to help bony ingrowth and on growth. Historically, these would have been low yield processes, sintering processes or otherwise, porous plasma spray or otherwise. There's a clear win there where maybe the cost is offset, but there's a clear functional improvement. There's a better clinical outcome. You see this throughout, whether it be internal channels for conformal cooling with the tooling industry or otherwise. But is there a functional improvement where you need to solve it through additive? Another one could be supply chain reduction or supply chain efficiency. As we look at the way that metal components are historically produced, there's some processes in there that are there's some supply chain constraints there, especially in the casting industry, forging, otherwise, where you have a lot of consolidation in these industries, and sometimes it could take months, if not years, to get a certain part. And if we're able to streamline that through additive, almost thinking of additive as a mini foundry, there could be some upside there. And the third one that we'd almost want to look at is part consolidation. When we're looking at part consolidation, are there a series of processes that we can consolidate into one? So we have a series of tubes that we're doing some machining steps, we're doing some laser welding, we're doing some sort of having a number of components that all have to come from their own internal source. Can we streamline that process and find some functional optimization while streamlining the overall part consolidation? And then the final one is kind of a no-brainer, and it's used ubiquitously throughout the industry, but lightweighting. With the advancements that we've had in computational design and really the ability to design in ways that we haven't been able to before, we're able to lower weight of components while increasing strength, and it's kind of a no-brainer. So topology optimization in these things, especially key in like the motorsports, space industries, where it's going to cost what, 50 grand to throw a kilogram of something into space. It needs to be strong for about 8 minutes as it gets into orbit. How do we do this, and how do we optimize? And it's fairly ubiquitous, and it's not just for space. I think we want to think about it with other industries as well. But if we can answer one of those four questions and find some optimization with metal additive, can you reduce tooling, all these things? That's sort of it's a matter of your opportunity cost as well as sort of the financial burden and the technical burden to bring it in. Does it make sense? And what we always want to avoid is just using metal additive, because some executive wants to. It needs to solve an application problem.
Yeah, I think OEMs are quite straightforward with this. They're not going to use the technology just because it's a fancy or a trendy term or so. At the end of the day, the application itself needs to justify the investment in it, isn't it?
Absolutely.
Great. Well, Jeph, you've covered an abundance of subjects I want to ask you 1,000 questions about. But before I just do, Elena, would you like to answer the question as well?
Yeah, thank you. So I absolutely agree with the facts that Jeph mentioned before. I would like just to include also some other considerations. For instance, it can happen that a company thinking about introducing AM to the production chain already has AM tools included in the production chain. That's what we see here, especially in the European market. As I'm talking about, especially, for instance, the example of laser cladding. We have an incredible amount of companies, especially in Germany, on the automobilistic sector that are already working with tools that are AM able, let's say, in the 2D level for wear resistant coatings or laser cladding, joining and whatever. And then with just a relative small investment could be able just to do 3D printing themselves, or to move maybe for a 4-axis configuration to a 5-axis configuration or whatever. So they may require a relatively small invest and be able to operate in a wider range. So this is one aspect. And the second aspect it's interesting to be mentioned is the topic materials and the possibility of do your own materials, to do in situ alloying, to move to a multi-material approach that is not cannot be done on a conventional approach, graded structure, sharp change between materials that can be just done by additive manufacturing, taking or avoiding other processes like joining that can lead also to a worse performance. And obviously the cost, it is a high topic or a hot topic on additive, but there are already studies or use cases where you can see definitely from weight reduction or from the increasing functionality that the costs are more beneficial if you do a certain amount of parts or a combination of parts with AM. So that's it.
Yeah, I really think we're only scratching the surface with materials. I'm glad you brought that up. It's really, we're using, I think a lot of the materials that we're using are potentially even subpar because it's conventional casting materials that everybody knows and loves. But as you get into some of the higher end things, I think we have the ability to do some really cool and innovative things with the material side, for sure. Glad you brought that up.
Yeah, and it's definitely a topic I would like us to go a bit deeper into. But for now, let me just ask this, I guess, relatively simple question, which is, okay, we're manufacturing in polymers quite a lot in additive manufacturing. And 3D Printing Service Bureau or so is quite familiar with the calculation of the return of investment. There are actually quite straightforward equations that, depending on the number of parts one needs to produce and the cost of the materials and the machinery, etc., they can understand whether it's worth it going through 3D printing technologies or other like injection molding or so. So with plastics, most of the times it can be simple. With metals, however, and that's what Jeph shortly covered, we're talking about a complete different approach when it comes to design complexity. Because as you said, with topology optimization, there are hollow designs that you wouldn't be able to do before. And it's not just a case of how do I produce this part either in this technology or the other, but rather I can produce this part. And this is a part I couldn't do before. And I've seen this personally quite a lot in the aerospace industry and the automotive industry. What's your experience with this?
I think, yeah, so, there's definitely different barriers to entry. With a lot of the plastic stuff, you're not necessarily producing an end-use part. So obviously, where the industry began with rapid prototyping, maybe we need a functional design, but maybe, you toss it outside for a couple days and it completely falls apart, things like this. Whereas what we're really looking at with the metal side of things is generally end-use parts, whether it be from tooling or otherwise. So as we're looking at it, I think there's a few key places we win that we already talked about. One that we kind of didn't talk about is the tooling aspect of it, right? And this is where we've seen a lot of wins in metal already. Is do you have a low volume, high differentiated product? So do you have a lot of part numbers and you're not producing hundreds, thousands, or millions of them, then it starts to make sense. But really, it always comes down to the application for me. What problem are you trying to solve? And that's what we really try to always begin conversations with is, what's the problem statement? What are we trying to do? Because there are a lot of times where it doesn't make sense to use additive. And then you kind of need to look at the Venn diagram as you're looking into getting into metals as well. You have powder bed fusion, E-beam, laser. You have sort of the binder jetting technology of, Jonah would obviously know a lot more about that, or X1, which has a lot of good characteristics as well, especially when it comes to cost. And then you have some of the other, DED, FFF types of technologies that are great for repair, maritime industry, really, really big parts. So what of those is the right place to go? Because there's give and take, and I think as the industry continues to grow, we'll likely see more consolidation of these things. 10 years ago when I first started, I started on really, really early E-beam, the first two, RCAMs in the States. And back then we thought that there was this huge void between E-beam and laser, and now it's consolidated to a large degree, where they're both fast. You can print high resolution on each. So it again comes down to the application. What machine tool is right for the application? What process is right for the application? And I think as we go forward, we'll be able to see some really interesting things as far as what can be moved as far as materials, process control, and the rest.
Thank you. Interesting. I believe in the meantime we got Jonah back.
Can you hear me?
Bit more than yeah. There's an echo. Do you want to try again?
Yep. Let me.
There it is.
Now. It's perfect now. So yeah, can you hear us? Because we can hear you perfectly.
Yep, I can. Yep, I can hear you. Okay.
Awesome. We're ready to rock and roll then. Welcome back. Glad to have you. We were just going over basically the decision-making process of someone who wishes to adopt metal additive manufacturing. Jeff's point was that it massively depends on the application and the part itself and so on. Is there something you would like to comment on that?
Yeah, that's the first hurdle, and that's a really good point that we all go through every time we engage new customers that are trying to get over the barrier to entry. What do you print? And the first parts that are proposed are always parts that are being currently manufactured one other way in some other traditional method, whether they're cast or machined or stamped. Those are usually the first parts that are brought to or proposed to being 3D printed without any changes. And that's always a difficult thing to do, to start with a part that's been designed for a different type of manufacturing. Because as engineers, we design parts as much for their application as we do for their manufacturing process. So, it's difficult to take a part that was designed specifically for die casting and say, apply it to 3D printing. So if you can get over that first hurdle and begin to look at all the way back at the design and at the application and redesign the part for 3D printing, and again, for your method of 3D printing, whether that be binder jetting, or SLA, or any type of FDM process, then you apply different rules to the design of that part. And one of the beautiful things is that a lot of those design rules are relieved when you start to look at 3D printing processes, and those constraints are lifted. So you can begin to apply things like the generative design that you were talking about. You can begin to combine assemblies together. Multiple parts can go into one single part, but that's it's difficult to see that unless you start at the very beginning. You can look at many sheet metal assemblies, and the reason that they are sheet metal assemblies is because they started with, how am I going to make this? And they decided sheet metal. And so they pieced 6 or 7 sheet metal pieces together in order to make the one static assembly that they wanted, when in fact, if you'd started over and designed it to be printed, it could become one part. So you begin to unlock that power that 3D printing brings to the engineer, but it is a hurdle because we've all gone through our training as engineers and design training, and learned how to manufacture these parts, these components. So whether they're plastic or metal or whatever they are, and the the skills that we've learned as engineers in university or beyond have taught us how to best design these parts with draft angles and with minimum wall thicknesses and everything that is important to manufacturing, whether there's an injection molding or stamping or you name it. You have to go back and relearn design for manufacturing for additive. And if you do that, then you can start to apply additive rules and you start to unlock the power, the potential. And then you can apply it, to your problem, to your particular situation, and things like being able to change the part design in the future, whether it's for improved performance, improved quality. If you notice that the part in practice is acting a certain way and you want to add a feature, you can do that in additive because you haven't invested in tooling. You can do that in the CAD file. Or if you've run the part and then you decide in the field that, oh, this geometry could perform better if this geometry was tweaked a little bit, if I tuned in my tolerances, that can be changed without modifying the tool. And then you can serve multiple customers at the same time by doing massively customized components. None of this is possible with traditional manufacturing. So again, I'll just go back to the beginning. You have to really go back and look at your problem and attack it from an additive perspective as opposed to a traditional manufacturing perspective.
I get the feeling that you must like 3D printing. Not sure, but I think you must do.
I do actually. And I grew up as a mechanical engineer, as a customer of 3D printing. And one of the reasons why we started Desktop Metal is because I really wanted to print in metal, and I never had the access to metal 3D printers as a young engineer or even as a student in university. Metal 3D printers were always too expensive or too complicated. They didn't want students working on them, or the product would be too expensive to be produced on a metal 3D printer. So yes, I love 3D printing and the power that it can bring you and the engineer. And so we're trying to bring that cost down. We're trying to bring the access up.
Yeah, certainly. Well, thank you very much, Jonah. Elena, my next question will be focusing on powder, because there's just so much about metal powder. But before we get there, is there anything you would like to add?
Not so far. It's fine. Yeah.
Great. Well, let's jump onto powders there, because I have so many questions because I don't know, and I think all of you guys have tremendous experience on them, so it would be very interesting. And I guess my question is very simple: what sort of steps does one take to verify the integrity of metal powders?
Yeah. So that's a very good question, and a very important one, because when we talk about additive manufacturing, we're talking about the entire process. And so it's very good that you're starting at the beginning with the raw materials. Otherwise, we would just call it 3D printing, right? It's just a 3D printer, but there's an entire process that goes beyond it, and before and after the actual 3D printing process. And before the 3D printing process in metal additive is the powder, and the powder supply and powder characterization. And it's very important that powder is chosen specifically for its performance, not only in the end product, so it needs to have the properties that the material needs to have, or it has to have the chemistry, but it needs to have the flow properties and the rheology that's important for the 3D printing process. So if that's the laser-based process, we have different powders for that. And if it's a lens process, there's different powders for that. And even cold spray, processes like Speed 3D, when you're spraying the powder, you want a powder that is going to work in that process. But let's take a look at the direct printing laser-based processes first. And so laser-based processes require a powder that is a very uniform size, and that is very spreadable so that you can create that layer, and then is very clean so that when you fire a laser into that powder, it melts, creates a melt pool that is pure as the chemistry, and is in an inert environment, and then solidifies and doesn't have contaminants or inclusions or anything in it due to foreign bodies or foreign contamination. So there's very important characterizations of the powders that are used in laser-based processes, even E-beam, slightly different. When you look at binder jetting has different constraints. So binder jetting, yes, we have to spread the powder to the point where we can then print directly on it. But that powder needs to be able to absorb the ink. It needs to be hydroscopic in a way where it the ink can penetrate it and glue it together, right? That binder ink. It also doesn't have to have the same cleanliness characteristics of a laser-based process, because what you're doing is you're gluing it together and then you're putting it into a furnace. And in the furnace, you can actually clean the powder. By heating it up to a certain temperature, you can reduce a lot of the oxide contaminants that are on that powder, and then sinter it to full density. So different powders, are required in different processes.
And we see, I think, over the last few years, we've seen a much wider availability of powder types as well as powders themselves. Elena, I think in the past you've worked on things like that. Do you want to tell us a bit about that?
Concerning the powder characterization, we have very strict steps that we follow at Fraunhofer. So it's really, especially for the laser-based processes, as mentioned, a very strict protocol, measuring density, flowability, rheological properties, oxygen content, contaminants, but also have interesting running projects where we try to characterize which is the amount of defects or satellites that it's good enough, I would say, to print parts that maybe don't require a special or perfect spherical shape. So, and there are also some low budget powders out there, especially in the field of research, that might be enough for the specifications required for laser metal deposition, for instance, and are cheaper, way cheaper than the used powders that we are all used to. And especially if you are not fabricating a high-tech part for space or aerospace, but it's a part for a tooling industry or with the requirements of mechanical properties that are not that high after some level, then these low-budget powders are an option. So that is something that we also take a look at while talking about powder characterization.
I see. Fair enough.
I think it's always following a risk-based approach. I think kind of echoing what the two others just discussed, but it's a risk-based approach, right? What are we trying to do with the powder? Because for different industries, there's different places. I mean, I would love to be able to use metal injection molding powder on a laser powder bed machine for the tooling industry, because cost is king there, and then we can compete better with our friend in the lower right corner. But for certain other applications, if we think about reactive materials like titaniums and aluminums for end-use parts, then things like powder reuse become summarily important. And the way that your powder starts isn't always the way that it ends. So what's the lifetime of powder, and then how do you assess the usability of the powder over time? So it's one, important to specify the beginning of the powder, and the deposition quality, the chemical constituency, all these things, and what rolls up into those characteristics. But it's also super important to intelligently design a powder reuse schema for the application, for the organization that's using the tool, based on that final application, so whatever that may be, and then to characterize it, right? This can have huge implications when it comes to return on investment for when you're buying a printer for, they're expensive. Let's be real. Metal printing is not an entry level thing. But if you have to throw your powder away after every use, or you can only use virgin powder, man, that's going to have a huge implication on the overall price of your part, and there's going to be very few applications that work. But if you can use your powder limitlessly, that has, again, huge implications on per part costs. You got to be thinking with additive in general, but certainly with metal additive, you don't have an economy of scale, really. There's your variable cost is fairly fixed. And as many parts as you can cram on one printer, that's kind of your economy of scale. So if your variable cost is if you're able to limit your variable cost by being able to reuse powder longer, from soup to nuts, that can have massive implications on the financial modeling of what parts work. And then the tool, from a machine tool aspect, we're able to, there's a broader set of applications, and all the things that we talked about with design can be applied more widely.
Yeah, it's a very good point, because I mean, as you said, there is a massive relevance with cost, and purchasing a 3D printer, metal 3D printer, is not a decision that you can just simply make overnight, usually. So I guess it would be interesting to dig a bit deeper into the whole concept of make or buy. We see there are a lot of marketplaces out there. So should one fully integrate metal 3D printing in their company, or should they keep buying parts from the marketplaces that now make it easier and easier and more affordable to get the final part straight to your door?
So I guess maybe I can start with that. I guess from the point of view of Fraunhofer, there is no universal answer for this question. So it depends especially on the application the company is pursuing. As I mentioned, it could be that there are already introduced printers, 3D printers at the company, like a laser cladding machine that can be used again. It can be that that's what we usually see also when companies come to us, that the company did not select the appropriate technology to print the part that they have in mind. So my suggestion would be, first of all, maybe to go to a service provider or research institution that can offer some support on the choosing the right technology, or maybe doing some redesign of the part, introducing some features and functionality so that this part is really an interesting part for additive manufacturing, that you have a certain amount of advantages by doing this part on 3D printing. So before just buying a machine by yourself or making huge changes in the production chain, I would say, as my suggestion would be to try to look at a service provider that has experience with that, or a research institution as mentioned, and see if you can maybe do a group of parts with the same process, or definitely introduce the advantages we mentioned before, lightweight, cost reduction, and so on.
Fair enough. Yep. Thank you. I get the feeling that you want to add something, Jeph.
I think echoing the same thing. It's really, you got to prove out the design concept and prove out the application. So I do. I think it's nice. It's a nice opportunity to start with parts first. I've never seen machine come first. It's nobody's spending $700,000 on a machine on spec. It's always parts first, and having the ability to work with a customer from ideation to volume production, and then eventual knowledge and tech transfer, that's super powerful. It de-risks the entire process and the ability to bring in metal additive for the customer, and it kind of democratizes things for the service bureau. In the case of 3D Systems, we kind of do both. We sell parts and printers, so it's a unique opportunity, and I see it every day working with customers who, we've built tens of thousands or even millions of parts, and at some certain critical mass, it just makes sense for them to bring it in. And some customers just want to have that level of control, right? And
for sure,
they can innovate on their own too. So
yeah, it's a really good point, and I think that both Jeph and Elena were right on point. I mean, the answer is you want to do both, and I think if you're looking at 3D printing and additive manufacturing, you have a plan, or you're formulating a plan to bring manufacturing in-house, which is great. That's the first step, but you want to leverage the expertise of others as much as you possibly can, whether that's your distributor or the manufacturer themselves or a service provider. In that case, I think that you want to start by buying parts. You want to start by bringing in a printer and printing your own parts. And it's not like deciding as a company that we're going to, start making our own coffee in the building instead of buying coffee from the street. It doesn't just switch over like that. So you need to get started right away, but you also want to see what the end product of a good end product looks like. And so a service provider can provide you with that as well.
Yeah, that's fair enough. Guys, we have a bit over 5 minutes left until the end of the panel. So what I recommend, considering our Q&A is pretty much on fire, is let's do a fire round of answers to the Q&A. And just a reminder to everybody viewing right now, Jeph, Jonah, and Elena will be at the networking event, the networking session right after this. So feel free to speak with them directly there too. But for now, let's just go over the questions. So first and foremost, first question would be, when do we see copper and aluminum becoming a mature material set for metal additive manufacturing technologies? Who wants to jump on this?
I will take this, I think. I do see already a certain maturity for those materials. Maybe we should need to change the mindset and talk about maybe wire technologies. We can control much better the reactivity and oxidation problems that aluminum, for instance, brings with it. So we can switch to the wire LMD technologies that are there and are also quite mature. On copper, there are different solutions on the green laser level, and infrared laser is not that convenient due to the very low absorptivity, but we have machines over there and applications like inductors, heat exchangers, even rocket engine with aerospike nozzle, usually made of Inconel, but also some approaches moved in the direction of pure copper alloys. So I see a drawback definitely in the powder bed level on the laser-based technologies on the building chamber size for copper. So far, there are not really big building chambers, and we are a little bit limited there. I also see a lot of opportunities for binder jetting due to the absorptivity problems. And I think on that, probably Jonah can comment much more than me.
John, I get the feeling there, if you want to go on.
No, I'm glad that Elena took the question right from the beginning, because Fraunhofer has the expertise here when it comes to these very difficult and challenging materials. And it's a great question and a great point, because traditionally those two materials have been very challenging. Copper, very challenging for laser-based systems because the absorption of light, it's very difficult to weld that copper powder together. And aluminum being so reactive, it's very difficult to put aluminum into a sintering process and get a fully dense, stable part through a binder jet. Now, using other types of sintering processes like press and sinter, traditional manufacturing has been very successful in commercializing, like a press and sinter aluminum, but that's not the case. You don't have that luxury to press the parts together and break that oxide layer that lives on the aluminum. And in laser-based systems, the aluminum needs to be very oxygen-free when it goes through laser printing. But like Elena, I'm very positive, and I'm seeing a lot of progress in sintering processes like binder jetting. Copper is a great fit. It's a great fit to put the copper through furnaces and reduce the surfaces, clean the surfaces, and allow the part to fully densify. And aluminum, on the other hand, aluminum is a tricky one that we're working on, and can't wait to show some of the technologies that we have for some aluminum. But I'm very, very excited about the future of aluminum and additive, because that is the material that that everyone asks for.
Yeah, we're definitely bullish on aluminum with the vacuum chamber concept, especially. So lots there with AP Works and the Scalmalloy alloys, and then Elementum 3D with the metal matrix composite models. Really cool stuff going on there. I think we're only scratching the surface with high strength aluminums. They were super frustrating 10 years ago when you just get the hot tearing, and they're just impossible. And you've got pretty much subpar materials, frankly, in the aluminum, especially in laser powder bed. that are castable aluminums, but are subpar to some of these others. And I think we're seeing a huge acceleration, especially on aluminums. I'm bullish on copper as well, but we've fried enough optical systems with copper that we're taking some different paths there. It's challenging for sure.
Well, looking forward to having the same chat in 5 years to see how different things will be then.
Absolutely.
Hopefully less.
Until then, let's take advantage of the remaining 2-3 minutes that we have. And if you guys could answer the following, which I think is a question many people have. Do you see a bright future for metal 3D printing with FDM, or FFF, as many call it? I don't know, John, if you want to take this one.
Sure, yeah. So absolutely. So FFF printing of metal is very new. It's one of the newest. And it opens up the door to to printing metal parts in ways that have never been possible before. And the obvious one is in the office. I think over the course of the last 20, 30 years, we've seen 3D printing evolve in multiple directions. So polymers have gone from huge machines that live in factories down into smaller and smaller machines that now we can buy for our kids. And we use at home. But metals have not, right? Metals evolved into the other direction, into larger and larger, more sophisticated machines that live in factories and build parts for jet engines, which is rightfully so. This is where the demand was, and this is where the opportunity lied. But the future of metal, we need to begin to unlock that type of polymer printing for metal. And FDM method of printing metal does just that, right? It allows users to use an FDM printer to create fully functional metal parts. Now, what we're seeing is that metal FDM is being applied to tooling and fixtures and low volume prototyping, low volume manufacturing support. But this is exactly where FDM lives, right? This is where we see factories and engineers, embracing FDM as a printing medium to build fixtures and tooling and looks like, feels like, fits like parts. And now you can add to that functions like parts. And I think we're going to see the design cycle accelerate significantly because you're able to so easily print metal parts that function.
You're on mute. Filippos, you're on mute.
Yes, it happens. I was just saying, Jeph, Elena, if you have any comments to add, please feel free. Just a reminder, if you could be quick, because we need to move on to the networking session.
Maybe just a short comment on that. Obviously, one of the advantages of the nozzle technologies, if it's one of these, is to print big parts. The problem or the constraint with the FFF technology is obviously that you need sintering allocated after that. So some of the advantages of printing big parts with these nozzle technologies are not there. So that maybe DED technologies, laser metal deposition, would be more convenient for big parts if you're thinking about metals than this metal FFF. But as Jonah also mentioned, this is a very promising technology that we need to follow in the future.
It's all part of this larger Venn diagram, right? There's time and place for everything. And repair some maritime things, it makes a lot of sense for really big parts. And I think over the next 5-10 years, we'll see some consolidation of these things where you'll probably be able to print laser powder bed, e-powder bed, much larger, and you'll probably get finer resolution with some of the DED, FFF types of technologies. Same with the binder jetting. We'll see improved process control and the rest. And we'll continue to see as things mature. We'll get one machine tool will be able to do more things, yes. But I don't think you're going to have one that just does everything.
Sounds perfect, to be honest, but well, at this point, I would like to thank you all very much for being part of this panel. Thank you for taking the time, and of course, thank you for answering the questions from the audience. I can see on the Q&A there are still a lot of amazing questions, so guys, viewers, please do feel free to go to the 3D System lounges, to the Desktop Metal virtual table. You can find Elena as well. You can chat with them directly. So feel free to reach out to get these questions answered. And thank you all so very much. Jonah, Elena, Jeph, appreciate it. And let's go on to networking again.
Let's go find Zach.
Thanks.
Yeah,
Where'd Zach go?
Cheers, everybody.
Bye.
Great event. Bye-bye.